All right. So thank you everyone for coming to today's seminar. It is our privilege today to have Professor Eun-Gook from KAIST talking about instability of J=3/2 Bogoliubov Fermi surfaces. Eun-Gook did his PhD at Harvard with Subir Sachdev, and then went to Santa Barbara and Chicago before moving to KAIST 5 years ago. He's done a lot of really interesting work on quantum criticality, superconductivity, and topological phases. And today he'll be telling us about Bogoliubov Fermi surfaces. So thank you, Eun-Gook.
Thank you very much for this kind introduction and invitation also. It is my great pleasure to give a seminar here. And so today I'll tell you about instability of J=3/2 Bogoliubov Fermi surfaces. Before getting started, I want to tell you, if you have any question, please interrupt me and ask me a question. So here is my collaborator and references. So my entire talk will be based on this paper recently published here. And so this is my student, Hanbit Oh. This is the picture where she took at the March meeting this year. Unfortunately, it is canceled, but she took the picture. So here is my outline. So first, I'll give you motivation. I think I'll give you pretty long introduction and motivation part. And I mainly discuss exotic phases of J=3/2 state. So J=3/2 state has been quite familiar to condensed matter theorists. With probably the simplest example with J=3/2 state with S and P orbitals. Probably one of the most well-known example is gallium arsenide. In this case, we know spin-orbit coupling is pretty strong. And this textbook, so I took this band structure from this textbook, and the part you need to see, you need to focus, or you need to pay attention is this gamma A state. So this gamma A state basically forms 4 degenerate state. So in terms of J, is a 3/2 state. More recently, mercury telluride become quite popular because this is the candidate material of the topological insulator. Typical band structure of mercury telluride as a bulk is shown here. And as you can see, at the gamma, again, we have a 4 degenerate state, and this 4 and different from the gallium arsenide, mercury telluride have this quadratic band touching. So both of them have a quadratic band touching, and one of them is inverted band structure. And this J=3/2 state, or these 4 degenerate states, are protected by time reversal symmetry and cubic symmetry, which means unless we break either time reversal or cubic, this degenerate state, this touching point at gamma, cannot be repeated. So, to break, so to kill this J=3/2 state at gamma, we need to either break time reversal symmetry or cubic symmetry. But we are dealing with the sp orbitals in gallium arsenide and mercury telluride, so symmetry is usually not broken. So in weak interaction, we always have symmetric phases. So this degeneracy, 4 degeneracy, are not repeated. So then we want to see some interaction effect. So probably one of the popular way or easiest way is to introduce not S and P orbital, D orbitals. So D orbitals are more localized, so Coulomb interactions are more stronger than S and P orbitals usually. In this sense, people found so this pyrochloride structure, so the chemical formula is A2B2O7, and this pyrochloride structure hosts d orbitals, and so it has a strong Coulomb interaction and spin-orbit coupling because we are dealing with the transition metal, 5d orbitals usually. So the pyrochloride structure is like this. So A side, we have a corner sharing tetrahedron structure, FCC structure, and B side is basically same structure, but it's slightly shifted. The candidate material element for A side is green, B side is blue. And among them, pyrochloroiridase are probably one of the most popular materials. So iridate, in this case, B side is iridate, and iridate has an iridium 4+, which means that we have 5 electrons. Because of strong spin-orbit coupling and cubic symmetry, we have eventually J effective 1/2 for each iridium atom. So what it means is that in this tetrahedron, so if we consider one tetrahedron, at each side we have an iridium atom, and we can treat this iridium atom as a 1/2 spin. So what it means is that in total, for each tetrahedron, we have A state in a tetrahedron. And because we have a cubic symmetry, this A quantum state must be splitted into the representation of a cubic symmetry. And if you do a little exercise, simple exercise, then this A states can be written as a 2, 4, 2. So this 4 state is basically nothing but J equals 3 half state. And this 4 state is basically the same state as in gamma 8 in gallium arsenide or mercury telluride. So one of the nice part of pyrochloroiridate is that this pyrochloroiridate hosts J equals 3 half state, and at the same time we have a strong interaction because we have d orbitals. So we can expect more interesting physics driven by Coulomb interaction.
Okay. Sorry, I'm a bit confused. Why we have 4 spin 1/2? Why is it not 16? Why is it 8?
I'm sorry. I can say again.
Sorry, 4 spin 1/2. Why is it not 16? Oh, I have a problem with counting. If I have 4 spin 1/2, 4.
Yeah. So, okay. So
2 power 4. Yeah, right.
Okay. So let me say it again. So this pyrochloroiridate, the unit is a tetrahedron. So if I choose one tetrahedron, at each vertices, we have one iridium atom.
Yes.
Okay. Then this one iridium atom, because of this 5 electron, so this is the final energy diagram with both spin-orbit coupling and crystal field splitting. And then since we have a J equals 3 half, we basically fill up this 4th electron, and 1 electron stays in J effective 1/2. So we can treat iridium atom at each vertices as a local state J equals 1/2 spin.
Yes, but there are 4 vertices, right?
Right. So which means that I have 2, 2, 2, 2. So A state in a tetrahedron.
I see. You just add them. You don't multiply them. I see.
Right. So
I see. Okay.
So then we can we can split this.
Yeah.
Okay. So nice thing about this pyrochloroiridate, at least some material, they are having many experiments. One of the most popular element is this prosidium iridium oxide. And here, even RPAS has been done. And this RPAS shows that about quadratic band touching effect. But there are some interaction effect. And because of this interaction effect, there are some uncertainty. and more interesting signature in other experiment, but at least there are some signature which shows that this particle iridase is close to this quadrat band touching physics. Okay. So then, theoretically, so in this particle iridase, there are having many proposals, theoretical proposal with a symmetry breaking. Many topological phases were predicted. Topological insulator by breaking cubic symmetry, or by Bar-symmetric or Dirac-symmetric by breaking time reversal symmetry, or if symmetry is not broken, which means that both cubic and time reversal symmetry is present, this Coulomb interaction becomes strong, and some non-Fermi liquid type behavior appears, and it is also proposed. And there are having many other proposals about theoretical proposal and experimental investigation. So bottom line is that so this particle iridase hosts many interesting exotic. So there is a possibility for to host many interesting exotic phases. But in these cases, everything is about normal phases, so not superconductivity. So in this talk, I want to consider some exotic phases or exotic, especially exotic superconductivity with J equals 3/2 state. There has been nice experiment, and one of them is actually from University of Maryland. This paper was published, I think, 1 or 2 years ago. So they consider J equals 3/2 state with a half Whistler material, yttrium, platinum, and bismuth. Here, strong spin coupling is there, and invergent symmetry is slightly broken. And what they found is that they find the superconducting state beyond the triplet. And they conclude that superconducting state has line order gap structure. Okay, another motivation, in this case, theoretical motivation, is from this paper. This 2017, the 3 gentlemen basically proved the existence of exotic superconductivity with J equals 3/2. So when I say exotic, what do I mean by exotic superconductivity is as follows. So in this talk, I'm gonna say conventional superconductor for the superconductors with a gap structure with a full gap or point node or line node. I know usual textbook conventional superconductor only consider this, but I'm going to treat these 3 cases as a conventional superconductivity. When I say exotic superconductivity is like this. So here we have a nodeless structure, point node. So there's one point. And in this case, it's a line node, so nodal line. So exotic superconductivity means that the nodes forms Fermi surfaces. Okay, so this yellow is a Fermi surface. So the Fermi surface of Bogoliubov quasi-particles. So that's what I mean by exotic superconductivity. So I want to emphasize here, we do not break translation symmetry. Okay, so their proof is quite interesting, and I think is educational. So if you're interested in, I would like to encourage you to read this paper. So their setup is as follows. So they assume existence of invergent symmetry. So it's a central symmetric superconductivity. And also they break time reversal symmetry. So with these 2 conditions, they show Bogoliubov Fermi surface is possible by considering non-interacting Bogoliubov Hamiltonian. So the way they show is that they show this Bogoliubov Fermi surface is protected by topological invariant, G2 topological invariant. Because of this topological invariant, this Bogoliubov Fermi surface is allowed, at least. Okay. So then, in this paper, even they propose some possible candidate materials, especially in heavy fermion, this heavy fermion system. And this heavy fermion system also shows some signals of time universal symmetry breaking. So this is a Kerr rotation.
Can I ask a quick question?
Sure.
So does the inversion symmetry actually play a role in the topological protection here?
Yeah.
It does, okay.
Yeah, it's very important. Okay. So after this paper, these authors also wrote some paper about non-central symmetric superconductivity, and they found some examples of the possible Bogoliubov Fermi surface, but they cannot prove the existence of Bogoliubov Fermi surfaces or this Bogoliubov Fermi surfaces. But once we assume the existence, once we assume the inversion symmetry is there and time inversion symmetry is broken, then one can prove the Bogoliubov Fermi surfaces is possible. So this is a non-interacting Bogoliubov Hamiltonian. So we can basically diagonalize everything. Then because of this condition, we can classify energy state. And then one can prove that we can define the G2 topological invariant.
Great, thank you.
Any other question? So this is a nice paper. So yeah, this is a nice paper. Right. So there are many candidate materials for this Bogoliubov Fermi surfaces. Of course, experiments are difficult. And many people are trying to find this exotic superconductivity. And one nice news is that at least some material shows some indirect evidence for this Bogoliubov Fermi surfaces. So this indirect signature is nothing but the specific heat. So this material is iron selenide, doped iron selenide, and TC is TC is a 4.5 K, so probably around here. So this state is superconductivity. But somehow they find some residual specific heat residual contribution, which indicates the Fermi surface, or at least zero energy state. Loss of zero energy state in this state, in this material, in this system. And also 214, this infamous material 214 shows some signature, but it's controversial material. So I don't know, I think this material may be better. Yeah, it's a nice system to look at. Right. But again, this is indirect because this residual contribution basically indicates the zero energy. We don't know it is localized or delocalized, so we need more investigation. So after this, these work, they were having many other works, lots of papers appeared and published. But I would like to say that most of these work consider non-interacting Bogoliubov positive particles. So, or they just use the Ginzburg-Landau type approach, phenomenological approach. So in this talk, the main question I want to address is that what happened if this Bogoliubov positive particle or Bogoliubov Fermi surface have some interaction effect. So main question is that once we have Bogoliubov Fermi surfaces, and so the Bogoliubov quasi particle from this Fermi surfaces must interact with each other. So one Bogoliubov quasi-particle, other Bogoliubov quasi-particle, they must be interact with each other in nature. So they cannot be just non-interacting. So there must be some interaction. And the question we want to ask is that whether this interaction kills Bogoliubov Fermi surface or not. So that's the main question. So this is basically quite similar to the question of BCS superconductivity in metals. But there are some similarities and differences, and I want to answer them in this talk. So our strategy is pretty standard. We will use mean field theory and also renormalization group analysis. And implication of our investigation is that we consider interplay between symmetry, inversion symmetry. Topology means that G2 invariant of Bogoliubov Fermi surface and interaction effect. And like I said before, I will compare instability of this Bogoliubov Fermi surface with BCS instability of metals. Okay. Okay, so that was motivation. Okay, so I will first consider one Bogoliubov pair problem. So basically following the Cooper strategy. So Cooper studied one Cooper pair problem on Fermi circuit, on metallic Fermi surface. So in this case, in our case, we consider central symmetric superconductivity, which means that we have an inversion symmetry. And because of inversion symmetry, we can, so this is the central symmetry Bogoliubov Fermi surface. So this is the Fermi surface. And at Fermi surface, we can consider one Bogoliubov quasi-particle state, so K alpha. And because we have an inversion symmetry, we can consider inversion partner. So K and minus K, and some other degree of freedom like spin or angular momentum is the same. So then we can consider Bogoliubov quasi-particle and its inversion partner. And then the question is that this inversion partners form bound state or not. Okay. So then in terms of structure of problem, it's quite similar to the Cooper pair problem. So if we consider one Bogoliubov quasi-particle state, and this superscript 1 is for the to describe one particle Hamiltonian, and this is the inversion operator, and K becomes minus K. And then this bound state problem can be written like this. So this is a two particle state and energy. So it's basically Schrödinger equation. And then we can solve this Schrödinger equation by introducing gap equation. And then gap equation's structure is like this. And if you believe me, and it's quite similar to the original Cooper pair problem, the answer for this eigenvalue problem is this. So here alpha is for the angular momentum, basically, number, and L, here L is interaction channel. So we only consider one channel to get this energy, eigen energy. And important thing is, as usual, this minus sign means the bound state, and this exponential form. Okay. So, so this simple calculation tells us that bound state exists if we consider one Bogoliubov pair. So, so this. Okay. So it's quite similar to the Cooper pair problem. So then we can compare what's similarities and difference between our one Bogoliubov pair problem and one Cooper pair problem. So Cooper pair on metal is that we have an electron Fermi surface, normal Fermi surface, and we consider time reversal partner. And this time reversal partner basically breaks U1 symmetry. Okay, so then superconductivity appears, and most of the time we know this Fermi surface becomes almost gapped. So for the S wave, it's a completely gapped. Some higher angular momentum gap structure is partially gapped. Okay. Then we just consider one Bogoliubov pair problem on Bogoliubov Fermi surface. So then what we show here is that we can consider inversion partner. So then we can guess maybe inversion symmetry is broken even we consider many particle system, many particle pair problem, many pair problems. But I want to mention that probably more interesting question is that whether this inversion instability accompanies with the gapping condition of this Bogoliubov Fermi surface. And that I will answer in the next few slides. Right.
I have a question.
Sure.
Yeah, so when you consider the pair of Bogoliubov quasi-particle, you only draw, you only draw like those lines for those top patch and the down patch. So I'm just wondering, for those Bogoliubov pair, can they come from this stripe in the middle?
Oh, yeah, of course.
Just want to make sure that, okay, thank you.
Yeah, so this is just for illustration.
Okay.
Yeah, it's even here, there, anywhere is possible. And that's the subject I'm gonna consider next. So this is I choose a one Bogoliubov pair. Now I'm gonna consider all Fermi surface. So in all Fermi surface, at each K, there is an inversion partner. So we can consider all Fermi surface problem. So this is the two-body problem. So now I'm gonna consider many-body problems. Okay.
Thank you.
So I have another question. So what you're considering is the residual interactions left after superconductivity has set in.
Yeah.
And so what is the motivation for considering the Bogoliubov quasi-particles to have attractive interactions, residual attractive interactions?
Mm-hmm.
Usually when the interactions have resolved and superconductivity has set in, it's not clear whether the residual interactions will be repulsive or attractive.
Right. So that's a good question. So so to answer that, okay, so at least I cannot guarantee that the residual interaction is always all channels attractive. I cannot do that, but at least I can assume that one channel. So if I believe this Rottinger theorem, not Rottinger theorem. What is it? Latino Criteria. So you know, in metallic system, if we there should be at least one channel which has this attractive interaction generically. So if I use that logic, then I can guess, or I can assume that at least there is a one channel which becomes negative or attractive. Then the possible logic I can use is that I can do the RG calculation, and I can show that recursive channel, even in this case, becomes marginally irrelevant, but the attractive channel becomes marginally relevant. So then I can conclude that this Bogoliubov pair problem, so this attractive interaction becomes more and more important, at least at low energy scale, if there is any one channel. So
okay, thanks.
Maybe that's correct.
Can I ask a question regarding the BDG Fermi surface? Because I mentioned that people have defined a Z2 topology environment to characterize the Fermi surface. I'm wondering if this Z2 topology have any like boundary feature or something like a bulk boundary correspondence with for the topology.
Right. Okay. Yeah. So the this is the gamete system. So the for the gap state, we can distinguish Burke and boundary clearly, and then this Burke boundary correspondence usually useful and quite effective. But in this system, so the Burke state is basically delocalized, so there is no gap, and then boundary and Burke are basically mixed in that sense. But still, there are some non-trivial structure, and I think people have studied a bit, but it's more, in my opinion, it's more difficult to more difficult than the gap topological state.
I see. Thank you. I have another question regarding the measurement, because you only mentioned there are like some specific heat measurement for the BDG surface, Fermi surface. I'm wondering if the BDG surface will respond to RPAS measurement, and is there any like experiment evidence using the RPAS to detect such kind of Fermi surface?
Right. Good question. So the RPAS. Right. So this, I think this is too low temperature for this material. This is a quite. I think there are some RPAS measurement, but there has been no report to claim that Bogoliubov surface is observed in RPAS. But yes, certainly if temperature range is okay, then yeah, RPAS will be one good tool to observe this Bogoliubov surface.
I see. Thank you.
Okay.
Sorry, hi, I have a question. So can you repeat again? Can you go to your previous page? Right, so can you repeat again why for this Bogoliubov Fermi surface case, there is an inversion instability? I thought it's gonna be still a U1 instability because there's a superconductivity, but
Right. So this, Cooper pair on metal basically forms a or this Cooper pair basically breaks U1 symmetry.
Right.
So then this inversion partner forming this inversion partner. So here basically the remaining symmetry is only G2. So inversion, sorry. So in this system, the main remaining symmetry is inversion symmetry. So the symmetry is very low. And then we can, and I'll show you how inversion symmetry instability appears.
So when you say inversion instability, do you mean in the same way as the U1 instability that it's gonna spontaneously?
Yeah, right. So, this U1 instability is basically connect this K and minus K.
Okay.
And yeah, and they break the U1 symmetry. This forming, and then this inversion partner basically forms the inversion breaking order parameter. So,
okay. Yeah, thanks.
Sure. But there will be a very significant difference between these two problems. Similarity is that here we have a BCS type, a BCS logarithm for this U1 instability. And this inversion instability, I'll show you that we also find the BCS type logarithmic instability. But here, Fermi surface is mostly gapped. And we found that Fermi surface is not gapped generically. So there is always remaining Fermi surface, even without inversion symmetry.
I see, thanks.
Okay, so I'll discuss inversion instability of all the Fermi surface. Okay, so the here is my model. The model is a normal part. Is basically start with this quadratic band touching type physics. So I have this quadratic band touching, and then I can put some chemical potential here. So this is chemical potential, and this is the basically Latinger Hamiltonian. So Latinger described used this type of Hamiltonian to describe gallium arsenide and mercury telluride and many other materials. Then we want to have a Bogoliubov Fermi surface. So I'm going to consider special or typical pairing to realize Bogoliubov Fermi surface. So this is a time universal symmetry breaking quintet pairing. So the form is like this. I will not explain the meaning of these gammas or these C's, but you can believe me, or you can look up the paper if you are interested in. So this is a normal Hamiltonian to realize this quadratic band touching Hamiltonian with a finite chemical potential, and this pairing with this pairing and normal part, and we can consider this BDG Hamiltonian and diagonalize, and you will get this Bogoliubov Fermi surface. So this yellowish line is the gaseous. Is basically Bogoliubov Fermi surfaces. So this calculation, so here, so this is the 4x4 Hamiltonian because we consider J equals 3.5 state. So this is a 4-band model. So this one band is a 4-compound spinner, and with number basis, this is an 8x8 Hamiltonian. Okay. So since we, it's useful to consider symmetry. So we have a charge conjugation because of supercontinuity and parity, so inversion basically. And this is a transformation. Then one can prove that with this charge conjugation and parity, energy at the same momentum, energy and sorry, so something is, so there's a typo. So energy and so is the pair, the plus and minus energy appears simultaneously. So this should be comma, sorry. So and because of this structure, I'm gonna introduce basically 2-band model. So at each K point, we have a plus and minus, which can be characterized by this tau G. Pauli matrix. So the reason why I can do this is that basically at each K, we have a plus and minus pair. This is they should appear. Okay. So what it means is that even though I start with this 8x8 BDJ Hamiltonian, because of this charge conjugation and parity symmetry, I can write down effective 2-band model because at each point energy appears as a pair plus minus. So I can introduce this tau G. And then Bogoliubov Fermi surface condition is that this energy becomes 0. And that's okay. Right. Good. Now we want to couple this inversion order parameter to this effective Hamiltonian. So this tau G, so this is the Hamiltonian without inversion order parameter. So I'm going to use the phi for the inversion order parameter. And then what we found is that this phi can couple to this like this. This part is important. So phi is obviously inversion order parameter, which means that phi becomes minus phi under inversion. And in this case, inversion symmetry acts as a trivia in Pauli spinor space, the spinor space. So what it means is that we can only have this tau 0, tau x, tau y. Tau g component is killed by charge conjugation. condition. Okay, and then this rho naught, rho x, rho y have several possibilities. So since they inversion odd, this is there are many options on x. Okay, so if I have an inversion of the parameter, so this effective Hamiltonian means that this is the only possible channel. So there is no tau g. Okay? So so you can show this quite easily. So basically, by using this symmetry transformation, one can prove charge conjugation. Here is rho g component. Rho g. Okay. Right. Question? No. Okay. So then, so this is Bogoliubov Fermi surface effective Hamiltonian. Okay. And then we can introduce generic interaction between Bogoliubov quasi-particle. So then this interaction can be, so this is a superconductivity basically. So we can, it's difficult to expect the long-range interaction. So then probably short-range interaction is enough. But in any case, we can consider this 4-point interaction terms with some channel information, G and V. And for simplicity, maybe we can consider a separable interaction. Then we can consider this K prime separable condition. And this is the inversion odd part. So yeah, so then we can consider possible channels for this generic interaction, and this is the possible channel. But for simplicity, I'm gonna consider only 0 and X component, and it's easy to generalize. So right, okay. So then with this interaction structure, if this interaction is big enough, we know then this symmetry must be broken. And in this case, maybe we can choose order parameter phi with some channel information, so mu and k here, and mean field. And we are going to do mean field analysis, so we can use the self-consistent equation. We can obtain self-consistent equation by using this. Right. Then by doing mean field analysis, so this is the standard mean field analysis. So we start with the non-interacting Bogoliubov Fermi surface Hamiltonian, and then this interaction by doing this mean field analysis becomes like this. So the linear term, quadratic term, and this is a straightforward mean field analysis steps. Okay. So then this mean field Hamiltonian becomes basically quadratic Hamiltonian. So one can diagonalize this by transforming these spinors. Then one can find this result. So by doing conventional unitary transformation, we can find the so one can write down the mean field Hamiltonian like this. Right. So then this the ground state energy of this mean field Hamiltonian can be written as epsilon naught phi plus here ek phi can be either negative or positive. So when it becomes negative, we should add this contribution. But if it is positive, we can just we can just ignore. So this is the ground state mean field ground state energy with the order parameter phi. So if phi becomes 0, then this becomes always positive. So this can become 0. So then with this mean field Hamiltonian, what we can claim is that Bogoliubov-Fermi surface condition is that this energy eigenvalue E is 0. Then if we only consider 0, tau 0 and tau x component, then this is the explicit expression. So EK is that original Bogoliubov-Fermi surface energy eigenvalue, and then this is a tau x component, so there is a square root, and tau 0 component comes like this. And because of this minus sign, it can be either positive or negative. So if tau 0 is gone, then this term is 0. But if, because in our system we have a tau 0 component, so we have this condition. And epsilon naught phi is this expression, and there is a minus sign. Okay. And Bogoliubov-Fermi surface condition is nothing but that this energy function is 0. Okay, so then since we have now mean field ground state energy, we can do conventional instability analysis. So we can compare, we can consider difference of ground state energy. So different means, which means that so with the order parameter phi and without order parameter, then we can consider whether this is negative or positive. So the ground state is ground state energy is lowered or not. And then one way to check BCS type logarithmic divergence is that we consider this basically substitutability of order parameter. Then what, as you can see from this structure is quite similar to the BCS superconductivity, and then one can prove there is a logarithmic divergence. Okay? So what it means is that so by using this effective two-band model means a tau G effective Hamiltonian, we can show that inversion symmetry becomes unstable. Okay? So the theoretical structure is very similar to the Cooper pair problem. Okay? So basically, with this generic Hamiltonian, with the mean field interaction, with the mean field analysis, we can have a tau 0, basically tau 0, and tau x, tau y, and this tau x and tau y basically plays the role of Cooper pair in the Fermi surface problem. And similarity happens here.
Hi, Eun-Gook. Can I ask a question?
Sure.
So what is the form of rho x here?
Rho x, okay, so yeah, so rho x, rho, yeah, so rho x, rho, okay, so this form factor, so I can call this form factor. So this is basically inversion odd function, which, yeah.
Right, so do you consider like ks plus ky, iky?
Yeah, that's also possible. Yeah, so inversion odd is enough. So the inversion odd is the only condition for this rho 0, rho x, rho y. And which channel is favored is that depends on the system's interaction. So basically, this interaction form determines rho x, rho naught. Right.
I see. Thanks.
Sure.
A quick question. So when I'm considering the superconducting symmetry on this Bogoliubov Fermi surface, should I still be considering spin 3/2? Or because now you're just using a 2x2 Pauli matrix.
Right.
Your tau 0, tau x, tau y is sort of like the usual spin 1/2 spin triplet superconductivity. Can I do it that way?
Yeah, so the only condition we need is that inversion odd.
Okay, yes. Mhm.
That's, so as you said, so we start from the J equals 3/2 band structure. So,
Right.
so when I project onto this tau G, what it means is that basically all the spin channel, 3/2, 1/2, minus 1/2, minus 3/2, they are all mixed generically. So then the condition we need is that inversion odd.
So naively speaking, so if you have 3/2, don't you have to consider, I don't know, a 4x4 gamma matrix instead of a 2x2 Pauli matrix
Yeah.
or something?
Yeah, that's the original setup. Yes, exactly. So this is the 4x4 matrices.
Right, but that's the normal part. I'm talking about
That's the normal part. So
how about the pairing symmetry though? The pair. Oh, yeah. So your delta should also have a 4x4 spin structure.
Yeah.
I see.
Yeah. Sorry, I was too fast.
Yeah. No, it's all right.
Yeah. So then, so the total BDJ Hamiltonian is 8x8. And my pairing is also 4x4. So this is also 4x4. So total 8x8. And then, so then we are interested in only low energy physics. So then what I can do is that from this condition, I can project this 8x8 Hamiltonian down to the 2x2 Hamiltonian.
I see.
And then, like I said, all the spin informations are basically mixed.
I see. Okay, so you're only looking at the two lowest energy bands.
Yeah.
Basically, okay, yeah. Got it.
Because I'm interested in instability.
Right. Yeah, makes sense.
Yeah. Okay, good.
Quick question.
Sure.
So I think the inversion order parameter are, since they are all odd inner inversion, does this mean that the resulting state is, even after the inversion instability, could be still like gapless or topological, because it's like something similar to a P-wave pairing, something like that?
I already mentioned that. Yeah. I already discussed that. Right. So from this simple calculation, what we showed is that so in this central symmetric Bogoliubov Fermi surface, if we introduce infinitesimal interaction, attractive interaction, then inversion symmetry is broken. So it is inversion instability. Okay, so that's the message of our calculation. Okay, so then, so this inversion instability indicates that at least for the ground state, inversion order parameter must be non-zero. Non-zero. Okay, so then if we recall the Bogoliubov Fermi surface condition, this condition is that the eigenvalue of mean field Hamiltonian is 0. And then if we only consider, for simplicity, 0 and x component, this was the condition. Okay. So for the ground state, inversion symmetry is broken, so phi is non-zero. Okay. So then, if you staring at this formula, what you can conclude is like this. So we have three-dimensional vectors, kx, ky, kz. And to achieve Bogoliubov Fermi surface, we need to satisfy this condition, this equation. So then what it means is that we have a three variable, kx, ky, kz, then one constraint. So then what it means is that we have generically, we have a surface. So this is only possible because this is non-zero. If tau zero component is absent, then this becomes zero. So the right-hand side becomes zero. So if right-hand side is zero, then what happens is that we need to satisfy two conditions. So one is this one, zero, and this one is zero. But because of this tau zero component, this simple equation only contains one variable. So in what it means is that in three-dimensional space, we have only one constraint. That means that generically we have a surface unless we fine-tuned this dx rho x, d0 rho 0. So that's the one. That is a one way to see why there is a Fermi surface even without inversion symmetry. So our logic is that inversion symmetry is broken eventually in central symmetry over Fermi surface. But even though inversion symmetry is broken, Fermi surface structure is generically survive. And the way to see this structure is that basically boils down to the presence of this tau zero or rho zero component. Okay, question? So, yeah. Okay.
I'm sorry, I have a question here. So if the Bogoliubov Fermi surface is gapped, then it saves more energy, right? So energy,
yeah, it saves more energy.
so energetically, it is favored instead of surface if the inversion symmetry is broken.
Right. Yeah, so there is some, right. So you are saying the energetic contribution.
Right.
Right. But the, right. How do I answer this? So probably maybe right.
So you said that the rho. Sorry. Go
so
ahead.
Yeah. But this energy argument usually
right. So when you do the mean field calculation,
right.
I guess this kx plus I ky, something like that, the imaginary component will be favored because it will gap out all the Fermi surface, all the Bogoliubov Fermi surface. If you consider only kx or ky, then you will have not on 9.
Right. So yeah, so then this question is actually go back to the whether Bogoliubov Fermi surface, central symmetric Bogoliubov Fermi surface is even possible or not. So so if you use an energetic argument, then fully gap state is usually favored. But depending on the interaction, some interaction favors nodal structure. And that question is a quite difficult question to answer precisely. But at least in terms of possibility, so if we, so that, my whole argument or my whole result are based on the presence of Bogoliubov Fermi surface, central symmetric Bogoliubov Fermi surface. So
yeah, then you start with a material with inversion symmetry. So there is topological reason that the Fermi surface is stable. But here, if you break this topological reason, then I guess it will not have Fermi surface.
I'm not sure. So this simple analysis. So my analysis is quite simple. So if they based on only mean field
right.
research. And then this mean field result at least tell me that Fermi surfaces usually exist. And then, of course, we did some simple tight binding Hamiltonian, and we checked generally Bogoliubov Fermi surface is survive. But you know, the previous work, it was hard to prove this, but I think our argument may add some more concrete evidence for the possibility of a non-central symmetry over the Fermi surface.
Okay, thanks.
Okay, it's ready. So then, yeah, as usual, we can do also RG calculation. So we can start with this effective Hamiltonian, and then we can consider some 4-point interaction. Then this is quite standard, and our conclusion is that central symmetry for Fermi surface becomes unstable, which is consistent of our mean field calculation. Then one can consider Ginzburg-Landau theory with this instability calculation. And for the Ginzburg-Landau theory, one can introduce a superconductivity for the Bogoliubov Fermi surface and inversion of the parameter phi. Then one can just write down phenomenal theory. Then depending on the sign of this order parameter energy, we can consider, we can imagine 4 cases. So the most symmetric part is a normal matter case. Then once we break the inversion symmetry only, then we will have a polar metal. And if we break the superconductivity or U1 symmetry, then we would have a Bogoliubov Fermi surface superconductivity. But this space transition may be maybe there are many steps, but for simplicity, we consider this situation. And then we can break both symmetry, and we have a non-central symmetry superconductivity. Then our instability calculation indicates that this R phi, so inversion of the parameter, tuning parameter R phi becomes basically at 0 temperature, it becomes minus infinity, which means that it's instability condition. So then with this phenomenological theory, we can imagine this situation. So at high temperature, we would have a normal metal. So at low temperature, we may have Bogoliubov Fermi surface superconductivity. Then if we lower the temperature, we would have 2 situations. The first situation is that at 0 temperature is at 0 temperature we have a central symmetry Bogoliubov Fermi surface. The other situation is that instability, inversion symmetry broken superconductivity. And then what the implication of our work is that this phase X is impossible. So this cannot be happen. So if there should be always this inversion symmetry broken phase, because this Bogoliubov Fermi surface always suffers from this instability of inversion symmetry. So this X space there is no X space. So then we only have this case. Then we thought about, so we tried to come up with the idea to detect this phase transition. So this is the inversion symmetry breaking transition. And then since inversion symmetry is checked by second harmonic generation, then to obtain or to measure this this inversion symmetry breaking substability, maybe we can apply strain gradient. Then maybe this divergence may appear around this temperature. Okay, so then this is my conclusion. So unconventional state appears with a J equals 3 half state. And Bogoliubov Fermi surface is protected by topology, and even with if we consider inverted symmetry, even one can prove Bogoliubov Fermi surfaces survive. Then what we did is that we consider Bogoliubov pair problem. Then we find the inverted symmetry instability, and then we find Bogoliubov Fermi surface may survive. Then inversion order parameter fluctuation must be enhanced in central symmetry Bogoliubov Fermi surface state. Okay, thank you very much for your attention.
I have a question. May I ask?
Sure.
Okay. So you mentioned this polar metal among other possibilities.
Oh yeah.
Okay. So can you give some this phase diagram, right? And can you give some simple physical interpretation for, say, one of those materials, for example? What is a physical picture of that polar instability? Can we understand it like in real space in a crystal? What is the meaning of visual meaning of this polar instability? Polar metal.
Polar metal.
It's like ferroelectric or something, right? No, I mean, is it?
Okay. So ferroelectricity, polar, it's easy to imagine because we can just draw this. But polar metal, so the K and minus K becomes different. Then, so it's a delocalized basically picture. So it's a metallic system. Sorry, I don't think I have a good intuition to picture this polar metal.
Yeah, because my thinking is that I also do not have any intuitive picture of this polar metal. But you see, if I had some visual picture of polar metal, then I could kind of mentally combine it with superconductivity and better understand, superconductivity with simultaneously with polar instability and all that. But because I do not have actually good picture, intuitive picture of polar metal, that kind of makes me difficult to understand, what is that Bogoliubov Fermi surface with polar instability on top of it. Yeah.
So Rashba Hamiltonian is not good enough to you, I guess.
What?
Rashba?
Yeah. But Rashba, I suppose Rashba is not a polar metal, is it? Rashba Hamiltonian is perfectly fine with me. I know that's the only thing actually I kind of understand the Rashba Hamiltonian. But it's 2 by 2, and but most importantly, it's not a polar metal, right? I mean, its inversion symmetry is broken because of the surface in Rashba, yes. Externally, yes. But I suppose that's not what you propose, right?
So, when I say polar metal, so I use this word very broadly. So it's a metallic system which breaks the inversion. Then how I break the inversion symmetry, I haven't considered seriously. So to me, at this stage, I just consider phenomenal square theory, which means that just consider any channel which breaks the inversion symmetry was good enough to me. So even Rashba is good enough to me. But I guess, but the better way to picturize the polar metal, I think we need. I need more intuition.
Okay.
Thanks.
Okay. Thank you.
Can I ask a question?
Sure.
So have you considered the effect of disorder? I mean, specifically the instability of gas disorder, because we know that the Luttinger semi-metal in the presence of a disorder interaction eventually is shown by Nankishal and her Messeron. They argue that there is no such apocausal phase whatsoever. So I'm just
right. Yeah. So disorder is of course a strong. So in terms of RG, disorder is a relevant operator. So that's for the even for this Collet-Banter chain. Also for this simple metallic system, if you do counting or do calculation, then you can see this ballasting metal becomes diffusive metal once you introduce disorder. So it's a relevant in that sense, it's a relevant operator. This question about the disorder in Bogoliubov Fermi surface is right. So it's important, and I don't think many people have studied this disorder effect seriously, especially with the interaction. That's the state, and maybe I can tell you my expectations. So this at least for this instability, Bogoliubov Fermi, so this weak disorder, I think it's okay, but strong disorder, of course, everything will be destroyed. That's because based on the PCS supercontinuity for the weak disorder is okay. So that's the reason why I suspect, I haven't done calculation, but I suspect this disorder effect is probably less important than inversion instability. Right, so that's my guess. Right, so what was the other question? So I thought you have two questions. One is a disorder, the other one is
no. The other one I was just mentioning the Latino metal case. Try to explain why I asked this question. But I actually have another question, very quick question. So you define exotic superconductivity in 3D by having, for those who have Bogoliubov Fermi surfaces. So in 2D, in your definition, there's no such thing in 2D. There's no exotic superconductivity in 2D. Is that correct?
2D, yeah, 2D. I'm not sure there is a proof, but I think people already proposed the possibility of Bogoliubov Fermi surface in 2D. So in that case, it's not surface, it's a line because it's 2D. So this, there have been several suggestions and I think one of the papers is almost proved, but I'm not sure. I haven't checked 2D system. But if we use the same logic, so I don't think that's impossible. So so certainly 2D is not. So yeah, 2D is probably okay. But I haven't. Yes, but I don't think there is a proof for the existence. If you can prove or disprove, that would be great. Yeah, 2D.
Thank you.
You know, this ion selenide is actually a layered system. So, no, not ion selenide. So some other layer system. I think people already discussed 2D Fermi surface in superconductivity without breaking translation symmetry. Right. That's the thing I know.
Could you please,
go ahead.
Yeah, okay. Could you please repeat the argument why in your mean field analysis the order parameter proportional to tau y is not considered? Because I think this seems important.
Tau y is allowed. Yeah, because so the reason I only consider 0 and x component is for simplicity. So tau y is certainly possible. So if we have a tau y, then I have this condition. Yeah.
So in this case, it's still like one condition such that you still have like a 2D Fermi surface?
Yeah.
And also, and when you mention that suppose if you just have rho x, but have vanishing rho 0 and rho y, and in this case we have like two conditions, right? So does this mean that we will have like a point node instead of a Fermi surface?
Right. So if right-hand side, if this side is 0, and to satisfy this condition, we need this E naught k is 0. And rho xk is 0, and rho yk is 0. then we need to probably we will have either point node or node list, depending on the structure of this function. So
Thank you.
So I had a question, kind of comparing the Bogoliubov Fermi surface case and the Cooper and the standard Cooper instability. So it seems like the important thing here is that, as you've pointed out, is the presence of this tau naught. So what's the physical reason that that's present in the Bogoliubov case but not in the BCS case? Is it a difference in symmetry?
Yeah, it's excellent question. So the I like this question. So, so if I consider BCS superconductivity, so then we usually consider Nambu spinner. Oh, so let's consider the simplest case. This, right? Danny, can you see this?
Yes, I see.
Right. Then the normal part. This normal part is tau z, because this is normal part. And if you do this calculation, sorry. Something like that. So this is the normal part. Okay. But if I consider, sorry, tau g, so then what you can show is that this is actually magnetic field. So minus is here, but the so this is the minus. Where is it? So this here is we have plus. So tau g becomes plus because it's a number spinner. Sorry, this. Sorry about my handwriting. This tau g.
Okay.
So what it means is that in BCS type superconductivity, tau zero component is basically proportional to Gman field.
Okay, but that's not the case.
Effect, basically, sorry, Meissner effect basically suppress.
Okay, but in the Bogoliubov Fermi surface case, I shouldn't think of tau zero as being a Zeeman field or anything like that.
No.
Okay.
So no. So that's because we start with this projective. So we start from the 8th band Hamiltonian, and our projection is basically mixed or the 4 compounds spin state. So then it cannot be the Gman field.
I see. Thank you.
Yeah, that's the crucial part, which distinguish this Bogoliubov Fermi surface case and conventional Fermi surface problem or BCS problem.
Can I ask a question?
Sure.
So you have mentioned this Kohn-Lottinger theorem, right?
Oh yeah, Kohn-Lottinger. Oh sorry. Oh yeah. So I was
right. I guess you point to this theorem. So have you checked for this Bogoliubov Fermi surface? Is this theorem still valid? I guess the calculation is very similar to the Fermi.
Yeah. In terms of calculation structure, I think almost the same. So just this zero energy condition is the only difference. But in terms of this, the zero energy condition is again comes from. Okay, let me clear this up. Again, zero energy condition comes from this, but the instability condition. So zero energy condition is special in Bogoliubov Fermi surface because of tau zero. but the instability condition comes from the tau x and tau y. And so in terms of calculation structure or the this divergence, if you want, divergence structure in RG, tau x and tau y channel becomes most important.
Right. So what about the cubic symmetry? I guess you just give it up, the cubic symmetry in the material, because the Condensed theorem, you have to distinguish different angular momentum.
Yeah.
But here you don't consider these cubic.
Right. So yeah. So the one way out is that Fermi surface is small, so I can for SO3 symmetry. But you're right. So for the cubic symmetry, I'm not sure even for this Condensed theorem in metallic system is still survive. So there, then I thought we need more conditions to have this Condensed type theory.
Yes, right. There are a finite number of representations.
Yeah. So then same thing happens here. So then what it means is that once we are worrying about the lattice structure, then we need, I think, further condition. But so the Hanbin, my student, what she did is she tried to connect from this A-band, so the A-band Hamiltonian with a Coulomb interaction, or some generic interaction in terms of A-band Hamiltonian, and try to project out down to this effective two-band Hamiltonian. And then what she found is that so the attractive interaction of the original Hamiltonian, the microscopic Hamiltonian 8x8, can survive down to this effective 2x2 Hamiltonian. So in that sense, we were pretty satisfied with this possible presence.
Great, thanks.
All right, are there any further questions? If not, let's thank the speaker again and for a wonderful talk and for staying up late for us. And thank you very much.
Thank you very much for your attention.
Thank you.
Thank you. Good to talk to you.
Me too.